hazard identification. The main thing that you need out of that for your project is HAZOP. For systems like what we design, a HAZOP is what we use to figure out what the hazards are. And then in chapter 12, for the risk analysis, for the complexity of the type of projects that we do, the plants that we operate, we generally use a layer protection analysis. And there's a lot of reasons for that. So today, we'll try to get through the hazard identification so that you can do a HAZOP for your project at some level. And then Thursday, we'll try to go through the layer protection analysis as part of that risk assessment, so that you can do a layer protection analysis at some level for your project, so that your safety person has something appropriate to talk about. And when we talk about safety for these projects, this is what we mean. This is what we mean, okay? So hazard identification, we talk about a process hazard analysis. Process hazard analysis comes from the regulations that are called the process safety management. And process safety management says you must do a hazard analysis, PHA. HAZOP is one of those, but it's not the only one. So we'll go through the slides and see what they say about it, and then we'll there's an example in the text that we can talk about where they do a HAZOP. So you've got non-scenario based methods. There's a checklist analysis you do. You do a safety review, you do an inherent safety review. Sometimes that's included in some other methods. You can do a preliminary hazard analysis. And preliminary is kind of where you're at with your project. And you do a relative ranking. So that's non-scenario based methods. That you should incorporate that as part of your project. And then you got scenario based methods, of which the HAZOP is one. So for the HAZOP, you go through and you try and you systematically look at different scenarios that could occur to cause the hazardous condition. Then there's fault tree analysis and event tree analysis, which are kind of looking at it from two different directions. One looks at the failure and sees what it could cause. The other looks at the event itself and goes back to what failures might have caused it. Then you've got a what if, you've got what if checklist. Checklists are really great as long as you can define all the things you need to consider, which is not true for our case. Most of our plants are way too complicated. You can do some checklists, okay? You can cover some things with checklists. Most of it is way too complicated. It also is the truth that all plants are different. There's not a single plant out there that's identical to something else. So you can't come up with a checklist that would fit every single plant. Then there's a bow tie, which is kind of a blend between fault tree and event tree. And then quantitative risk analysis is used. It is really a method to try to calculate the probability and the risk. But the problem with it for our industry is that it's just too complicated to do that analysis for an actual chemical plant. So that would be the ultimate, but you just can't do it. And then you got the layer protection analysis, which is a quantitative risk analysis, but we do it based on an order of magnitude. And we have some limiting assumptions that make it plausible that we can actually do a LOPA, but we cannot do a QRA. So you can do a LOPA and it gives you the order of magnitude risks that are associated with some hazards. Okay, so let's see. Non-scenario, we go through a little more details of the checklist. Here's an example of the checklist. So you would say, oh, is it properly laid out? Is there proper drainage? Is it adequate spacing? Do you have fire protection? Have you considered overhead hazards? Do you have headroom, storage for raw materials, clearance for power lines, that sort of thing. And this is great. This will get this, some usage. It'll eliminate some hazards. So I'm not saying it doesn't apply. It does apply. But it just doesn't, it's not something typically that's gonna let you avoid the largest risks for a process. And that's what we talk about with HAZOP, larger risks. You got safety reviews, that only works where you have people who are very familiar with the facility though. Same way with inherent safety reviews. It's hard to come up with a safety review if you don't, get a lot of experience. So doing a safety review is probably not gonna help you much for your project. Then you've got the preliminary hazard analysis. And this is very pertinent for your projects. So what are the hazardous materials and the plant equipment that's involved? You know what those are. Do you have a question about it? Do you know what they are? Am I just saying that? Do you know what that is for your project? Do you know the hazardous materials and the plant equipment involved? Who's doing the safety part of presentation? Anybody, any safety people in here? Okay, so for the safety people, what are the hazardous materials in your plant? What plant do you have? NGL. So what is a hazardous material? Like what specifically? Like propane. What else? Butanes. Butanes are pretty hazardous, will we agree? If you let the butane loose, it forms a vapor cloud and explodes. What about, do we have a safety person here from a crude tower? No? We don't have any safety people in here from a crude tower? You're gonna make me look it up? Oh yeah, he's just not admitting it, right? Okay. What's a hazardous material in your crude project?
The crudes?
Crude itself. What hazard does it have?
A whole lot.
A whole lot is not a good answer. Specifically, what's the hazard?
They're probably explosive of some sort or flammable.
I'll take flammable. I'm not sure about explosive, but I'll definitely take flammable. So that's your first step. If you're the safety person, identify the hazardous materials. Then you've got plant equipment. What kind of plant equipment can have hazards associated with it? So think about it.
Yeah, compressors cause issues if they like rupture.
Compressors, is that what you said?
Yeah.
Yeah, compressors, for sure. Pretty much any piece of equipment you bought, there are hazards associated with it, and you need to think about it. Then you've got environmental factors, emergency procedures, safety procedures. You need to think about that. If you're a safety person, hopefully you'll come up with something. Okay? Relative ranking, we're not gonna do, this is more for chemical systems than anything else. You go in and you say, well, what is the chemical that you're processing? And then they give rankings based on that. There's a Dow fire and explosion index and a Dow exposure index. And, we probably don't have much of that for our systems. You may have some H2S, but, in your refinery, I don't know if you have anything in your NGL that's a chemical. So I'm kinda gonna avoid this one, because we don't really have this issue at this point. Not to say I wanna ask you about it somewhere else, like in a test or something, but let's face it, the test is well after the presentation, right? So we have plenty of time to study this after we do our presentations. Okay, so you got failure modes and effects analysis, what if checklist, and then HAZOP. Those are scenario based. What is the difference between a scenario based method and a non-scenario based method? What's a scenario?
Situation.
We talked about scenarios before when we talked about relief valves. We said for each relief valve, you have to develop a scenario, because that's the only way you can figure out what size the relief valve needs to be. You have to have a scenario. This is something that happens, and therefore it causes this, and then I need to relieve this much flow. You know, that's the only way you can size a relief valve is with scenarios. So a scenario is like some sort of action that happens. It's an active thing. Something happens, and something happens, and something else happens because of that, and then something bad happens. That's a scenario. So these are scenario methods. The most important one to us is not this failure modes and effects method, but I guess we could talk about that. But it would be more like, not the what if or the what if check, it would be this one, the hazard and operability study. So we should probably spend more time on this one. So a hazard and operability study, what do you need to do a hazard and operability study? Where does it fit in, the hazard and operability study? What are you figuring out when you do a hazard and operability study?
Deviations from the design.
What you're trying to do is you're trying to figure out what scenarios exist that could cause bad things to happen. So you're actually considering scenarios. You actually create new scenarios in a HAZOP. These can take 10 to 15 weeks with a good facilitator for a unit. And we don't have 10 to 15 weeks, and we don't even have any good facilitators either. You know, there was a company that said they would come and facilitate HAZOPs for us, but I'm not sure we would gain much from it. Saw a presentation on that at the AICT meeting last fall, by a company that was doing that. They were more selling their software too, like software to do HAZOP studies. But they had facilitators that they would loan to companies for a price, who would go help them do HAZOPs, because it's a process that you learn. So we don't have 10 to 15 weeks. We hope to do some sort of, HAZOP. We also don't have PNID diagrams. So you would need a PNID diagram to do a typical HAZOP in a plant. Okay. So your HAZOP can't be as detailed. It has to be a preliminary HAZOP. This is how a real HAZOP is done. You get a detailed flow sheet, which is a PNID diagram, and then you it into process units, and you divide that into nodes with design intents to investigate parameter deviations. And they've got guide words, and you have to come up with possible causes. Those are your scenarios. And then the consequence of the deviation is, if it happens, that's coming up with the hazard. So you're saying, these are the scenarios and these are the hazards that could cause. Okay, that's what hazard and operability studies are. So here's an example of the guide words. No, not, or none, the complete negation of the intention, no part of the design intention is achieved, but nothing else happens. So, let's say we had a piece of equipment. What's a piece of equipment that we want to test this on? Somebody give me a piece of equipment you've got in your plan.
Saturator.
Saturator.
Yeah, saturator. Kind of mix it up.
No, I'm not sure what a saturator is. Talking about a steam saturator? Yeah. That's very detailed. Now, reboiler's probably a little bit less detailed, right? So I like reboiler for an example. What does no, not, or none mean for a reboiler? What's the design intent of a reboiler?
Put heat into the column.
Provide heat, right, to vaporize the bottoms. So what's the complete negation of that intention?
Not heating up the bottoms.
It doesn't work. Yeah, it's not vaporizing anything, it just stops doing that. That's your scenario, if you got a no, not, or none for your reboiler. Pretty simple, right? Got a column, got a reboiler, the reboiler doesn't work, stops working. That's the guide word no, none, right? So what happens to a column if your reboiler stops working?
Cools down, stops separating, everything goes down to the bottoms.
What?
Cools down, stops separating, everything goes down to the bottoms.
Yeah, it just stops separating, gets cold. Does it cause any trouble that you would worry about in terms of hazards? What kind of hazards does it give you?
Maybe if the
Lost
pipe,
your reboiler.
maybe if like the,
What?
maybe if like the exit, like piping can't support that sort of flow.
You have to be a little
Probably not
louder.
much. Maybe if the exit piping doesn't really support that amount of flow, but probably not much.
Yeah, well, I mean, you could come up with say, okay, my reboiler fills up, overflows. So you keep having feed coming in, reboiler stops working, and I can't get out the bottom because it's too much, and the reboiler, power overflows. You could think out a scenario like that. That would be a reasonable thing to think about, I think. But on the whole, you probably would struggle to come up with anything that would cause a big risk. A big event for a reboiler stopping working. On the other hand, what about a condenser? What if you did a no, not, none on your condenser? What would happen?
Something that would get a lot hotter.
It would get a lot hotter, and what would happen then? What goes along with heat in thermal tube?
Pressure.
Yeah, that's right. And so is that a problem if your tower just keeps increasing in pressure? Certainly at some point it would be, wouldn't it? So what's the risk then? What's the hazard? You lose your overhead condenser. I mean, you just
Pressure,
said it.
condenser, and then a paper cut.
Your
explosion.
tower over pressures,
Okay.
okay? Your tower over pressures. Hopefully you have a relief valve on it, right? But overpressuring your tower is not a good thing. But that's a scenario. So then you go on to the next one, more, higher, greater. And you apply that to the reboiler. You apply that to, so you apply that to whatever you're looking at, okay? Those are things you can do to your project. You know you have reboilers, you know you have condensers, you probably have compressors, you've got refrigeration systems. All these moving parts, you can use these guide words to see, well, what if this happens to this piece of equipment? Well, what if this happens to that piece of equipment, and so on. That's a HAZOP, okay? And these are just to give you ideas of what you can consider that maybe went wrong. So you need to go through and try to identify that. And let's see, they've got combinations, you know, flow, temperature, pressure, concentration, etc. You look in your book for this stuff. And then, here's an example of a HAZOP that they have in the book. So we got a reactor system, exothermic reactor. The design intent of the cooling system is to remove energy. Obviously, if the cooling function is lost, the temperature increases. That increases the reaction rate, and then more energy results, and the ultimate result is runaway reaction. So that's clear, that's for any exothermic reactor that you've got, pretty much. So they want to do a partial HAZOP using the cooling coil as a steady node. The process parameter of flow, the guide words are no, high, and low. No flow, high flow, and low flow. So we've got cooling, you see the cooling coil up there, and we've got cooling water in. What happens if there's no flow?
Nothing cools down the reaction, and there's a runaway reaction, so there's no.
Runaway reaction. What happens if there's low flow?
Same thing with slower.
Could be the same thing, right? And what if there's high flow?
Could quench the reaction, maybe.
Probably not gonna cause you terrible trouble, but it'll condense the reaction. Let's see what we got here. So, cooling flow, no flow. Loss of cooling, possible runaway. And then, in the HAZOP, they say, well, what are the existing safeguards, you know, what action could be taken? And then you also have to say, well, how did it happen? Because you're trying to come up with scenarios. So how could there be no flow? What could cause there to be no flow? What are the different things that could happen? What scenarios? They've got 5 of them listed. Could we have come up with 5 different scenarios that would have lost us flow? That's a HAZOP. Control valve could have failed to close. That's assuming it's a failed close control valve. Although even if it wasn't a failed close control valve, you could fail it closed by the controller failing it that way. You can fail it closed or fail it open, either way. There's always something that you can do with controllers. You can fail it either way. You can have plugged cooling coils that would cause a low flow or no flow. You could have cooling water service failure. It was a combination of those two. Well, that was low flow, but air pressure fails. That's assuming it's a failed closed valve. If you say the air pressure fails, but what we're doing here for the HAZOP is we're coming up with scenarios that would cause the problem that we talked about to happen. So they said, the flow could be no flow. No flow is bad, leads to runaway, and these are the possible things that we've come up with that would cause that to happen. And then so we say, well, what safeguard do we have? Well, we have a flow transmitter, we have a low flow alarm, we have a high temperature alarm on the reactor. Okay? Now you notice, there's no quantitative numbers here on the risk. This is just saying this is something that can happen. It doesn't say how often it can happen, what's the probability it's gonna happen, or what's the probability if it does happen that something bad happens, right? That's all a HAZOP is all we're doing is we're coming up with potential scenarios that would cause risk. If you're the safety person, or even if you're not, because I hate how the groups, you know, if you set your group up to where, oh, this person does this person does that, that person does it, then one person in charge of it is probably gonna be suboptimal. One person in charge of everything is suboptimal because one person's probably gonna do a terrible job compared to 2 people or 3 people. Plus 2 or 3 people would get more experience if everybody did it, right? So the student method of assigning individual items for individual group members is suboptimal for the individuals of the group as a whole. You don't learn as much and you don't do as good a job. That's a fact. And I can prove that. One student doesn't do as good a job as 2 students, and 2 students don't do as good a job as 3 students. I know that empirically. Okay, so you need a group to do a HAZOP. You know, a one-person HAZOP is terrible. So they at least have to pass it around. Have I made my opinion clear? Okay, that works for everybody else's class and everybody else's project, but it's a terrible approach to the plant design project. Okay. Anyway, HAZOP. You know what a HAZOP is now? Do you think you can do one for your project? You know, the first step would be to list all your equipment. And then the next step, maybe apply all the appropriate guide words to each piece of equipment and see if you can come up with something bad that happens. Okay? And then the next step would be, once you've done that, then you come up with possible scenarios that could cause that to happen. Okay? All right, HAZOP. Enough said, right? Then they have these recommendations, but these recommendations are not really helpful from a quantitative standpoint, but they are helpful from, if you do say there is risk there, this is the things that we can do about it, So later when you assess it with a layer protection analysis, a LOPA, and you look at these things, you say, well, this will help or this won't, okay? So the HAZOP can come up with a lot of things, a lot of recommendations. The downside of that is, if you go to HAZOP and you say, we ought to do this, or we ought to do that, or we ought to do that, the company has to respond to it. And the company would rather not respond to a bunch of, recommendations that really don't have any basis in probabilities or in reality, really. So usually in a HAZOP, you say, consider this, or consider that, or consider that, So later, whenever you do the actual risk analysis, you can look at it and you can use what is appropriate and not have to be tied into doing dumb stuff that costs lots of money and doesn't help, okay? Okay, so that's HAZOP. I've got a paper that talks about 7 column HAZOP, but I'm not gonna talk about that here. Do we have any questions about HAZOPs? Because HAZOPs are the main thing. You know what? We should do a HAZOP.
Thought you said we could because we didn't have any ideas.
I said we could not do one to the level of what you were doing with plans. You can do it based on preliminary information. Like this this thing that we did the HAZOP on, this is not a PNID, right? This is a preliminary grant. So this is like a process drawing, okay? PNID would have everything in here, and that's what you would need to do a full HAZOP. But you can do a partial preliminary HAZOP with what you know. So let's do one. The first step is we need to list all of our equipment. Okay? So we got two different, projects here. So I need a crude project, HAZOP, and I need an NGO project, HAZOP. Let's put this up. So who wants to go first, crude or NGO? Let's see, we got, well, thought we had 30 minutes, but no, we have about 25 minutes each. So we can do a 25-minute crude HAZOP, and then we do a 25-minute NGO HAZOP. Who wants to go first?
Crude.
Who said that? Are you on a crude project?
Yeah.
Are you ready to lead the HAZOP?
No.
Come on up, come on up. Come on up here. Okay, so you're on a crude project, right?
I am.
All right, so all the crude people have to help with this. See that Sharpie? Oh, it's not Sharpie, but the dry erase marker there. What we need first is we need a list of your equipment. So all the crude people, throw the equipment out at them. What equipment do you have in your project?
Desalter, that would be a changer before and after.
You got a tablet already?
No, I want you to list. We can draw one of them
Subway,
out.
subway.
Okay, we'll see how far we get to first.
Subway. It's shaking.
And, what do we have, like 6 of them?
Yeah.
You can just do one. I do want you to include the furnaces, right, that's important. We don't have revolvers, we have furnaces. And also your overhead condensers. And then you have various pumps, you have a lot of different pumps. So you got pump around pumps, you get feed pumps, charge pumps, all kind of pumps. What else do we have? Go ahead and put your pumps on there. You have pumps and control valves.
Is this okay right here?
Yeah, sure. Good work. Pumps and control valves. All right, so now, what we have to do is we have to come up with a design intent for each of these things. What's the design intent of the heat exchanger? Well, it depends on the heat exchanger maybe.
Heat or cool?
Maybe we can't just do a heat exchanger. Yeah, maybe we have to say which heat exchanger we're talking about. Okay, so let's pick a particular heat exchanger. Which one, what's your most, interesting heat exchanger? Okay, just tell me any heat exchanger. Give me a heat exchanger.
The one
Anything
for
is
salter.
Which
Your
one?
preheat recorded to salter.
It goes to sewage.
A preheat heat exchanger, that what you said?
Recorded to.
Yeah. So that would be like a pump around heat exchanger. Yeah. So put pump around in front of your heat exchanger. And then say which pump around it is. Just PA for pump around later. Alright?
Like the stage or?
Well, no, like, it's like you have three different pump rounds, don't you? Just pump around 1, 2, or 3.
One.
Okay, so one, we'll call one the one highest up in the tower, maybe. Okay, so that's the coolest pump around. What is the design intent of that heat exchanger? I mean, did you just put the pump rounds on there because I thought you had to? Because if that's the case, then, you know, we don't know why we did it, that's not good. We need to know why did we have a pump around in the first place?
To recycle heat.
It's kind of like a recycled heat, I don't like the recycle part, but yeah, it definitely does something with the heat. So, it's for, I mean, the purpose is for heat integration, is what it's for. Is that too hard? Is that too esoteric? Purpose, that's only the purpose of the pump arounds, heat integration. But it also does, you know, it also reduces the load on the tower. So you could say either one of them. Let's say, let's put it intent, the reason for it, the design intent is to reduce load on the tower. You're gonna have to do one of these for each of these. Right, so for the pump around one heat exchange, design intent is to reduce the load on the tower. What's the purpose of the desalter? What's the design intent of the desalter? To remove the salt. Did somebody say that?
Yeah.
It wasn't very loud.
I've been getting everything wrong, so it's not.
Okay, so remove salt, right? So you don't corrode stuff. What about, the crude distillation tower? I mean, that's obvious, right? What do you have a tower for? What's the purpose of the furnace?
To the heat. The bottom.
You need to come up with a design intent. I mean, why do we have a furnace?
To heat the
Furnace
Or
will
should we?
It's more than just heat it, right? It's to vaporize it, isn't it? So you need, so that's the first step. You need to list every single piece of equipment in your project and come up with a design intent for that piece of equipment. Cause you can't really, you do this process if you don't know what the, intention is, cause you see all this stuff that's, you know, intention, et cetera, that's all about the intention. So, and some of these don't apply, okay, so let's go back to one, let's go back to our feed pumps. What's the purpose of the feed pumps? I like that one, we'll make that one our go-to here, okay? If you tell me what the purpose of the feed pumps is, I'd appreciate it.
Create flow.
Transfer the feed.
Increase the pressure.
Transfer the feed? And the feed pumps, is there gonna be a control valve associated with that somewhere? You would think so, you would think you would put a pump, so draw a pump and a control valve where you're controlling, well, I don't see a control valve yet, but yeah, I mean, pump, whatever you wanna draw a pump as, right? Somebody help them out, where are we gonna put a control valve?
Yeah, somebody help me out.
Oh my gosh, is this a control problem? Is anybody in here taking control? No, I'm not taking control.
Restrict flow.
Anybody wanna help me?
Where are you gonna put the pump? Cause I see them sitting there on the entrance of the pump, but that is not where you wanna put a control valve, right? Put the control valve on the outlet of the pump, please. A control valve, you know what a control valve looks like, right? Looks like a bow tie.
Oh.
And it's got a, yeah, there you go. Alright, and then you got a little flow control, so that's good enough for now. But I would put a flow control measuring and open and close the valve, right? Okay, the design intent of that system is to provide feed, okay? So, no, not, or none. What bad could happen? Where's that feed go? And what bad could happen if we stop providing it? No flow, no feed. What bad could happen?
The
Tower.
so the boilers are just gonna start heating up the tower with nothing else to heat, so you're gonna cause some structure fairly.
Yeah, if, there's a lot of stuff in between, but when it goes to the desalter, then it goes over to what did it go next? Goes to a whole bunch of exchangers and then it goes to a furnace, right? So what happens if this pump shuts off feed and then you have no flow through the furnace?
Furnace just gonna heat itself up. Fail. Boom.
Did you hear him? What did he say?
I didn't hear him.
Not loud enough.
Furnace is just gonna heat itself up and fail.
Is that valid?
Do you agree with that? Anybody else agree with that? Why, I mean, we talked about this. If you stop the feed through the furnace, then the temperature that you measure on the outlet of the furnace is gonna start dropping, while the controller then will see that and try to put more heat into the furnace to try to stop it from dropping, not realizing that it may be dropping on the outlet of the furnace, but it's really hot on the inside. And then what happens? It's hot enough, what happens to metal when it gets really hot?
It bends.
It loses strength, and then you have oil that's pouring out all over the place inside of that furnace where there's plenty of fire, and so fire and oil, you get fire. You know, oil gets loose, starts burning everything. So that's what happens, or one thing you could say happens with no. And I've also gone through, that's almost like I've gone through the process of saying what the possible cause is. Well, no, I didn't say what the possible cause is, I said what the possible consequence was, okay? So the consequence of no flow then, we said it's, loss of flow through a furnace rupture, tube rupture, fire. Okay, that's consequence of our feed pumps, not doing what they're supposed to. And then, what is an existing safeguard so that that does not happen?
Probably gonna be a control valve on the furnace.
Excuse me, is it leak valve?
Relief valve's not gonna help you. What did you say?
Control valve on the furnace, you can set up.
Yeah,
a low
control
alarm
valve's not gonna
or low flow alarm.
really help you unless you know that it's happened. How is somebody gonna know that that happened?
An indicator,
What?
with an indicator, like a flow indicator.
An indicator, but how do they know that that indicator went to zero or dropped really low?
An alarm.
An alarm. Okay? So the existing safeguard may be a low flow alarm, just like what they said for this reactor. Okay? So that gives you some, a safeguard or two, action required, you can come up with that, but it gives you the consequence, because the consequence was, your furnace, your crude furnace is burning down. Now, the action, what do they take? Well, you're not an operator, maybe you don't realize what the action is, but I think you said something about shutting a valve, so, yeah, if you shut the fuel gas valve, put that in manual, shut it, so it doesn't keep ramping up the fuel gas, that's probably a good idea, right? Then it comes back to, what are your scenarios that cause this to happen? What's a scenario that would cause this, loss of design intent of the feed pumps to transfer feed? What's a scenario?
Something happened upstream, like maybe pipeline, something's, either there's pipeline rupture like upstream, like there's no flow going, or.
The valve fill close. Pump shuts off, pump motor goes bad on the pump.
You got a lot of them, right? So why don't we list them? Go ahead and, pick his up, and then he's got 2 or 3 of them. So what are the, scenarios? What's scenario number one? Scenario number one
Pipeline
was.
stops sending feed over.
Yeah, scenario number one was you lost your, I'm not sure it would be the pipeline, but,
So I guess,
it's coming from a tank, generally, the tank is not gonna be empty very quickly, but you lost suction somehow. This is something that honestly, these crew people that are gonna be our judges, they'll be really good at this part.
What did you say?
The valve fell closed.
Cause they actually see things like this happen, it'd be fresh. I've seen stuff like this happen, but it's been years, maybe decades.
The motor, the pump, the motor go bad on the pump. Shut off, I guess. That's a decent loss of stuff.
Well, yeah, that would be, but,
But no, the pump motor going bad is not the same as loss of suction. The valve fail close is not fail to close, but fail close. But why did the valve fail close? There's 2 different reasons. One, it could be a fail close valve.
Loss of instrument air.
Yeah, so if it's a fail close valve, it could be instrument air loss that did it. Or you can always fail close a valve if you say, well, the controller failed close. Okay? You can always say that. So then, we said we have one existing safeguard, right?
safeguard was.
What was our safeguard?
The
You didn't write it down, I guess.
An
What's our
alarm?
existing, yeah, an alarm on what?
Low level, right? Could be low level.
Low level? Somebody help us. Corey's bashful today.
Am I redeeming myself?
Yeah, you're doing good, but you're bashful today.
It's okay.
Ask him if he's in here.
Corey, what did you say?
Oh,
Alarm.
low flow.
Low flow.
And then what's the action that was required?
Make the valve fail open? Maybe, but that doesn't sound like very,
What?
make the valve fail open?
Well,
I feel like that could lead to further issues.
if you lose flow, that's the question. What is the action you take? Not saying we're gonna interrupt the scenario anywhere. You can do a safeguard. You were saying safeguard, make the valve fail open, that's fine. You can put that under safeguard. But I was saying, what's the action that's required if you lost flow? Reduce heat to the furnace. That's a good one. So, action required. It's an action required is another, up there, see up there on the list there? You got safeguards, you got consequences. We didn't list the consequence, though. No, we didn't. No, we didn't. Consequence, big fire. Big rupture, big fire. That was the consequence.
What was our action required? What, reduce heat to the furnace?
I think that's what it was. Shut down the furnace. Cut off that flow. Or if you lost flow already, you gotta figure that out. You can't get it back immediately. Okay. Whoever's in charge of safety, right? Do this for some of your more interesting and important equipment. Now, thank you. Erase what you put up there,
It was a pleasure.
and I need the NGL representative up here. We've got 30 minutes. We need an NGL representative. We need to do the same thing for NGL.
Yeah.
Oh, you're making these.
What do you mean, like for the slides, like switch on the slides?
We need NGL volunteer.
Oh, yeah, we have a meeting for it.
Okay, so whoever is doing NGL, raise your hand.
I'd say we could have a meeting.
Whoever's on the NGL group, already about half of you, right? Okay? So I just need a volunteer for someone who's on the NGL group to come up here and lead this, HAZOP. And it does not have to be whoever you assign as your student representative to do safety, because I think, like I said, that's terrible. Just putting one person in each thing, that's terrible. Suboptimal. I should just say suboptimal. All right. We got a volunteer. But you hoped in vain. Yeah. Okay, so first step, everybody help. What are the pieces of equipment for NGL?
I don't know if your group has a compressor, but we have one. Towers.
We're gonna have to be specific on the heat exchangers, though.
You wanna pick?
Cooling heat exchangers, heating heat exchangers,
You wanna pick?
because you have to.
Give me a specific example of a heat exchanger, that's what I'm saying.
Probably the ethane propane one.
I don't understand that, what do you mean,
The heat exchanger before the ethane propane separation.
We have a feed huge.
Okay, so
We might be
preheat,
different, but that would be,
so that would be a preheat.
we can either preheat, that's fine.
What other kind of heat exchangers do you have?
Cooling one and heating, several heating ones.
So you have overhead condensers,
Yeah.
you have reservoirs.
Right, those two.
What?
Riding the condenser report.
Yeah, well, you would consider it separate, yeah, so you have a overhead condenser, and then you have a reservoir. So you got a compressor too, so pick one. What about pumps? Do you have any pumps in this system? Did you look up and see what you can get it off of the pipeline for? What pressure they'll give it to you?
Yeah, that's what compressor is.
Do you have, if you have a compressor, yeah, okay, so you have a compressor to bring it up to
Yeah.
pressure? How do you control your compressor? I'm not sure we ever talked about that. How do
I
you
guess
control it?
increase, decrease power depending on what the outlet pressure is and if it's meeting spec.
Yeah, you really can't control the pressure by looking at the outlet pressure.
Or the pressure differential.
Usually what they do is they base it on the inlet pressure. So the suction pressure is responsive to the, turbine speed. So you'll adjust the speed of the compressor based on the inlet pressure. All right. So design intent, help us out here.
The compressor or the heat exchanger?
You gotta have a reason why you put that stuff in there, right?
Heat exchanger reduces the load on the towers by getting it up to temperature before.
Okay.
Compressor is get to proper pressure.
Or really it's to feed the unit. Isn't it? At the appropriate pressure. What's the design intent of the condenser?
Cool
bucks to the tower?
Plugs.
Provide boil up. So pick one. Maybe we should do the same thing instead of, so since we did the feed for the other one, maybe we should do the compressor for this one. So draw a compressor and a control system for it. What you can do is you can just put a, pressure controller off of the inlet. And have the, it measuring pressure on the inlet, and the output you can just go take to the center of the compressor. So draw a line, like extend this one a little more. Draw a line straight down to there, saying you're getting that pressure. And then take a line from here straight to the middle of the compressor. That will be your output. Okay, so the idea is that you adjust the speed of the compressor to achieve a suction pressure. That's the way, you can't control it by adjusting a valve on that like you can on the car. Compressors just don't work like this. Okay? So, the design intent was to what?
Provide-
Feed the unit?
Is the appropriate pressure?
Yeah, so what is the negation of the design intent?
Compressor's just not working at all, just flow straight through it.
What happens if the compressor stops? What if it doesn't achieve this? What is it? You know, what's the negation of it?
The outlet pressure, the pressure's just the, I guess the inlet pressure, so there's no pressure being added to the process.
Anything bad happen?
Powers are probably gonna be off spec.
Well, I mean, yeah, it's gonna be off spec. You're not making any product anymore. What else? What would happen if the compressor just shut down? Complete negation, right? You're going along fine. Well, what's the pressure of your pipeline?
200.
Okay, and then what's the pressure of your unit?
For us, it's 300.
Only 300?
Can you say that?
I might, I don't know what you said, it might be like 350, but it's only,
It is higher.
it's around there.
Okay, so what happens if you're running your unit, right, and you got this column, this column, this column, this column, pressure goes downhill, right? I mean, it has to, unless you have another compressor to pump it back up again. And what happens if you stop the compressor?
It keep increasing.
It's just gonna, would it not just flow straight through the compressor?
No compressors, no pressure keep increasing.
Well, the pressure increase.
It says compressor shut down, right?
Yeah.
So pressure drop.
Yeah.
If you didn't do anything else, what's to stop the flow from going backwards? And going back through the compressor, back into the pipe, what's to stop that from happening? You didn't do anything else. You didn't have any controls. You didn't have any safeguards, which is safe, the check valve is a safeguard. Nothing, and nothing was stopped.
Nothing until.
Okay, so that's the point, is when we're looking at this thing, we look at it in terms of this, possible consequence. Right? So that's where I would start. So, first we say negation of its intention. So So, no, it doesn't work anymore, no, none. Then what's the consequence? Well, the consequence would be
Potential backflow.
reverse flow for the unit. Now, and I'll tell you, reverse flow to a unit is really scary to operators. So it probably ought to be scary to us too, but I guarantee you it's really scary for operators. You may not think so, but it is, right? They really want that flow to go in the right direction. Cause if it goes backwards, what could happen?
Overpressure.
Overpressure, right? So you're compressing here. The pipeline may not be designed for that pressure that you're putting up into your unit. Okay, so if this fails and you get reverse flow, then whatever's on this side is now seeing the pressure that you are operating at. And do you think that that pressure is gonna go away immediately? No. I mean, you have towers, right? You have all kind of equipment. If that pressure comes back this way, it has plenty of, material to send that way to pressure that up. So what could happen on this thing? What's the consequence of reverse flow?
Overpressure.
Get overpressure.
Overpressure, yeah, overpressure the pipeline, overpressure the feed equipment. Now, we can go into existing safeguards, possible causes, or action required. Which would you like? The scenarios are the possible causes. We need to get there eventually. We need to have scenarios for why this would happen. But what about existing safeguards? What stops it? So existing safeguards, yeah, was a check valve. Yeah, those compressors, they have these valves too, that they try to operate when they stop too, because, what's another thing that could happen to the compressor if you had this reverse flow and your check valve wasn't working? What would happen if you didn't have that check valve to the compressor? You know? What do you think it'll do? It starts spinning backwards one. And what happens to a compressor? It spins too fast.
Tear itself apart.
It breaks. Kind of violently too. So, you know, another potential consequence would be compressor damage. Plus, those compressors have thrust bearings, and thrust bearings are generally in one direction. You know, it won't work too well if you try to run that thing backwards. You know, it'll break something if you do that very long. So compressor damage is a very real possibility. So, you wanna talk about action required or possible causes? Well, let's talk about action, because we're terrible at action because we're not operations, and so this is our worst one. So what's the action required? Well, we need another safeguard first, though. How do we know that the compressor stopped working? If you're on a plant, how do you know the compressor stopped?
If the inlet pressure and outlet pressure of the compressor.
Well, that's one way, yeah, but that's not gonna be very quick, you know, because the outlet pressure is gonna be bleeding back the other way, the inlet pressure is gonna go high, you know, but you may not have that, you know. Yeah, so maybe you'd have an alarm, on this inlet pressure, maybe you would, on the suction pressure. Almost certainly you would have an alarm on the suction pressure. But generally, when you have a big piece of rotating equipment, they operate by their own control equipment that's not, you know, it's not just a controller going straight to speed here. You would have a speed controller that's separate from that also makes sure that the compressor doesn't run at its critical RPMs, because that would destroy them. And that's generally a PLC of some sort. And it also has shutdown systems. If you try to run there, that it'll automatically shut the compressor down and shut all the valves around it. Okay, so normally, if a big piece of rotating equipment shuts down, then that PLC will tell you why it shut down. And then those are something they're called first outs. Because a lot of times when big equipment shuts down, then you've got this safety instrument system logic that starts shutting things down. There's a lot of different reasons why you can shut down a compressor. And so, but once you shut one down, then the logic, gets met for the next thing and the next thing and the next thing. And so pretty after just a very short period of time, within seconds, it's bam, 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 all the solenoid valves will drop and, you won't know what caused it, what shut it down sometimes. So these things generally will send what's called a first out back to somewhere where you can look at to see, well, what happened first, okay? Oh, God, that's what's neither here nor there, but that's kinda how you're gonna know. You're gonna know, because you're gonna get a shutdown button that comes up that says your compressor shut down. You're gonna get that, and you're gonna, you could have an alarm on the control, okay? So then what do you do about it? Compressor shutting down, boom, you got that alarm, what do you do? It'd probably do it for you automatically, but what would you do to stop the backflow? Well, what do you normally do to change flow? You got flow in a pipe, you wanna control that flow, what do you use? I mean, what do we use to control anything? What do we use to do anything in our industry? Pretty much final control element of everything in our whole plant is what? Okay, I'll go, how do you control the flow of water in your house? You open a valve or you close a valve. Valves are pretty much our final control element of almost anything everywhere in a plant or in a house or whatever, right? Okay, so the action required is you will close a valve. You'll have a valve here, right? Maybe you have a check valve there, but you'll also have a valve there. You'll close that valve. Now that may be a big valve and it may take a long time to close, but by God, you're gonna close it, okay? Somebody's going to anyway. You'd probably be doing it automatically, but that's what you gotta take. That's what the action you have to take. Okay? So then the last thing is possible causes. This is where we finally get to our scenarios. These are our scenarios that our HAZOP is designed to come up with. It's important to have the consequences, that's real important because you'll need that to figure out what's the risk associated with it when we do the LOPA on Thursday. But you also need the scenario so that you know what's the probability. What's the probability that this is gonna happen? So you need a scenario for that. So what's the scenario here that causes this thing to stop working?
Electrical failure inside the compressor.
Well, what's the driver to your compressor? Steam turbine. Yeah, if it's big enough, we saw that, right? If it's a small compressor, it could be electrical motor. If it's a big one, it's almost certainly a steam compressor. Like I said, there's a small ethylene plant in Groves that they use a gas turbine. So what can happen to stop your compressor from working?
Turbine,
Like a
The
steam.
driver stops driving it. Well, why does the driver stop driving it?
no steam.
Yeah, maybe it's a steam turbine and you lost steam. That's a scenario. Right? What else?
Motor, turbine, I guess.
Well, let's stick with whatever we chose. We chose a steam turbine. What else could cause it? control and you lost control, it's gonna fail. So we got loss of steam, but it's not as simple as loss of steam. You almost have to figure out, well, what's the scenario, you know, what caused you to lose the steam? To be a scenario, it needs to be, you know, what caused it? Electrical, that's enough, but then you have to say, well, what did that cause? So you got electrical, and that caused this, and you know, the scenario means, you might say, well, the electrical caused the PLC to fail, and then, you know, all the control valves shut or something, you know, all our steam control valve, the rack closed on those turbines. So you say that from here, the loss of steam, you might wanna say, well, why did we lose steam?
Boiler shut off?
What?
Boiler shut off?
Yeah, it could be your blower went out. Or if you're buying your steam from somewhere else, maybe they just, you know, they blocked you out. Maybe there was a block valve that closed or something. But you come up with a scenario for it, okay? And let's see. Oh, we pretty much covered this. Is this a big hazard or not?
Yeah.
Is destroying your compressor a big hazard? Could be. Most compressors are really expensive. Any part replacement is a long lead time. You're shut down for a long time. And believe me, that is very, very, very expensive. So yeah, it's a big deal. And plus, if the compressor breaks spectacularly enough, you know, you could lose containment, so. All right. Let's thank our, board. So now you should, well, you should erase this.
Yeah.
So if your safety, that's a start. That's your HAZOP. Okay? I don't want you to talk about PPE during your HAZOP. I mean, during your safety part of the presentation.
Yeah, everyone knows about PPE.
Well, it's just like, there's personal safety, and there's process safety. Personal safety doesn't belong in your project slide. This is process safety, okay? PPE is personal safety, right? Oh, if you want your test back, you can come by my office now, or you can come by, you know, tomorrow during